tonight's lecture is about so-called duality theory. And if I say something like a theory, that usually will scare you, like it will be highly mathematical. But I will try to avoid certain level of mathematical rigors, but try to just first explain the idea behind it. And first thing first, about the problem we are dealing with right now, I think you're all familiar about constraint optimization problem. Yes?
Can you make that alpha somehow? Focus interval?
This one, turn off this front light probably would work. Let me see. 1, 2. That's better? Okay. Okay, so hope that's good enough. If you want, you can, of course, adjust your seat to a better location, just maybe to see what happens. And we want to minimize some objective function that I call f of x, subject to both equality and inequality constraints. And this can be written in some standard mathematical form. For instance, we say there are m inequality constraints. Gi of x is less than or equal to 0. And there are p equality constraints. We call hj of x equals to 0. Okay, just for convenience, I want to say this decision variable x is n-dimensional vector that includes x1, x2 through xn. And also we have this f, which is a continuous function mapping from some n-dimensional real space Rn to one-dimensional real space R. And similarly, I would say this G is for each constraint is also some continuous function mapping from Rn to R for Gi and Hj for both equality and inequality constraints. And the feasible set, of course, can be the whole real space, but in general, it would be some subset of that, which I call x of 0. And this is just standard way of writing down the mathematical optimization problem. Any question about that? So if we say there are different ways to address this problem, in general, what we want to do is to construct Lagrangian multiplier for both equality and inequality constraints, right? By doing that, we are going to see, you're going to see some kind of functional like this, where you can say vector lambda is for the multiplier for what? The inequality constraint. And then my multiplier mu is for equality constraints. So this is just standard way of writing down the Lagrangian multiplier that connect both the objective function f of x and inequality constraint g, which you can say a collection of this gi, and then equality constraint h, which is a collection of this hi. And then this is, in fact, a function of both decision variable x and multiplier lambda and mu, right? Okay, so if you look at this Lagrangian function, which is a function of x, lambda, and mu, you might be curious why, for instance, we only focus on this x part, not the lambda or mu part. In fact, we could do that. And this is a function of x and mu. And x, lambda, and mu. And in fact, we have the feasible set for x. We should also specify what? The feasible set for the multiplier, right? And when we say feasible, that means what? For instance, this mu can be anything, right? Any real number. But this lambda, yeah, of course. It's a vector. It's mu. It's actually p-dimensional vector if we have p equality constraints. And then this lambda has to be m-dimensional vector. That's not the whole real space Rm. Why? Because we are talking about what? The inequality constraints. For inequality constraints, what condition do we need to satisfy? Yeah, this Quinn-Tucker condition, which says what? If the constraint is active, then what? Yeah, then this gi of x is 0, then lambda I can be positive, right? And then if gi of x is less than 0, which means the constraint is inactive, then lambda I has to be 0, right? So there are like two possible conditions for each constraint. And that's why overall we have these 2 to the power of m different configurations. But right now, if you talk about the feasible set, which means your multiplier lambda I has to be non-negative. So that's why I put this R plus, meaning that it cannot be negative. Okay? So now, if you think about the so-called primal optimization problem, is about this Lagrangian function L, where we only focus on what? Finding the maximum of this Lagrangian function as a function of x. Okay? And then, of course, alternatively, I can define so-called dual function, which means for fixed value of x, I try to find the minimum of this Lagrangian function with respect to lambda and mu. Well, that's a very good question. Right now, if you think about the original Lagrangian function, involves decision variables of both x, lambda, and mu, right? So in that case, you can say if I pick any value of x being fixed, I only try to maximize the whole function with respect to lambda and mu. Can I do that? Of course I can, right? It's an optimization problem. And for instance, I want to find the maximum. Would the solution exist? Sometimes it may not be. For instance, you may say, it's at some extreme point where it's not approachable. Then for mathematical convenience, instead of saying maximum or minimum, we just take the limiting point, like what I explained at the beginning of the course. We say the supreme or inferior of this. And then we have so-called the primal function and dual function.
So you mean that in this case, the primal function can take the value infinity and dual function can take the value minus infinity?
Yes. Of course, a natural question to ask is why we want to do that. Well, remember previously we talked about how to solve constraint optimization, like using Lagrangian multiplier. We just say take what, like the necessary condition is just take the derivative with respect to what? X, lambda, and mu, right? And set it to 0. And that's like the stationary point, right? And of course, by doing that, you get the necessary condition. And now it seems that we are trying to separate between what? The x part and the lambda and mu part. We say, well, for the Lagrangian function, we maximize with respect to this x, and then we minimize with respect to this lambda and mu. And then hopefully at the stationary point, if we have some solution, later we call it maybe x star, lambda star, mu star, that satisfy both primal and dual functions at the extreme point, then hopefully that's the solution to the original optimization problem. Okay, and then I think Lippy already asked the question, why? Why there's a hope we can do that, right? And that's a very good question. So in fact, if you look at the simplest problem, yeah.
Adjust the focus because I cannot see that clear.
Adjust the focus. Let me use this first. Let's see. How can I adjust the focus? Should I zoom? Not very clearly. Then let me see. How should I adjust? I don't think it's a focus problem. I think it's the resolution on the screen.
You cannot adjust something.
Well, I think.
You have the remote control for that?
Well, I probably can adjust, but the exposure probably won't really help.
Dr. Chen, you have the remote control for this projector?
Remote control for the projector? No, I don't. Is this slightly better? Probably that's. This doesn't really help. I mean, by changing the contrast, and I don't think it's out of focus. If this is. No, I think that's that's the best quantization level I can achieve to make it precise on this machine based on my heuristic search algorithm. Well. Well, I think that's probably the best I can do. And if you don't mind, maybe you can even move your place closer to the screen if you want to. I think that's. Yeah. Well, sorry about the inconvenience. And then I think Lippy will have a lot of burden to maybe polish the notes and share this with share this with your classmates. Okay, so right now I think it's natural that we have this Lagrangian function and then try to separate between so-called the primal problem and then the dual problem. The primal part, remember, is just if you fix lambda and mu, and then you can maximize Lagrangian function for x. And then the dual function is about if you pick any value x, then what? You can minimize with respect to lambda and mu. And then, of course, when these two coincide with each other, for instance, whenever you have so-called x star, lambda star, and mu star satisfy both primal and dual solution, then there's a hope that solution, in fact, is the optimal to the original problem that we are going to maximize, or we are trying to optimize. Okay, so now let's look at the simplest form of the problem, which is a linear program. In this case, of course, the objective function is a linear function of your decision variables. So this C, vector C, is just some constant. So your objective function is the inner product between C and your decision variable x. And then the constraint is what? Also a collection of inequality constraints. Why I don't care about equality constraints? Okay, and in fact, if you do have an equality constraint, I can also convert that into inequality constraint in such a standard form, so you don't need to really worry about that. Okay, so we have this constraint, ax is greater than or equal to b, and b is some vector which I assume is m-dimensional, and the decision variable is n-dimensional. So this matrix A is m by n matrix. Okay. So now let's talk about the Lagrangian function, this L of x and lambda. I write down the objective function, which is C transpose x, plus what? The Lagrangian part, which is lambda transpose of and the constraint b minus ax. Okay, so I have this function. And how do I solve the primal problem? The primal problem is what? Just you say for any lambda, I try to what? Maximize this L of x, Lagrangian function of x, right, with respect to x. And how do I solve the dual problem? The dual problem is like what?
What you have written is the dual problem.
I'm sorry?
The first one is the dual problem.
Well, the primal problem is solving for x, right? The dual part is like for any x, you try to first write down the dual function as a function of lambda, right? And then what? You minimize that. Okay? So if you think about, for this part, which is just the it's just the constraint and the objective function absorbed into a whole term, and then you have the inner product between C minus A transpose lambda and X, okay? And then this part, of course, we assume the decision variable is non-negative for X. And then how can we really minimize that? If you think about, this is the inner product between some vector u and x. I want to find the minimum. When would that exist?
You use that part C minus A transpose lambda.
Well, it's just some vector. If you say I have some vector, I do the inner product between some non-negative vector and another vector, I want to minimize that. I would say all the elements of vector U will have to be non-negative, right? Otherwise, if you have any negative element, then the decision variable can go to positive infinity. Then you don't really have a way to minimize that, right? So in this case, I will say this C minus A transpose lambda will have to be positive, which just says this A transpose lambda should be less than or equal to C. Okay? Yes? Okay, so what can we say about this dual function of lambda? If you minimize with respect to only this term, when this vector U is non-negative, the smallest value you can achieve is, of course, 0, right? When all these decision variables are 0, right? So I only left with B transpose lambda. In this case, we have A transpose lambda less than or equal to C. Otherwise, of course, this dual function is negative infinity, which will not really provide any meaningful insight to the problem. So what can we learn from this linear program? We can solve for x, right? But if we look from the other angle, we want to say what value of the multiplier will provide the solution to this problem. Then what? We have this part. So what's this? This is also optimization problem with respect to what? Lambda. And lambda is what? Multiplier. The dimension depends on how many linear constraints you have. Right? In this case, m. Okay. So let's say if m is much smaller than n, then what? You have another linear program with smaller size. Right? Let's say if my x vector is 10,000. I have 100 constraints. Okay, and now I convert that problem into what? 100 decision variables, right? And then basically, I just change the original linear program to a dual problem, which is also a linear program. And if I can solve for lambda, and then what? I put in to this Lagrangian function, then I can basically also find solution to x that maximize this function. Do you agree?
So is it a kind of problem transformation?
I'm sorry?
Is it a kind of problem transformation?
Well, yes, you can say a problem transformation. Well, it's a problem conversion, I would say, maybe. Just an alternative way to optimize a constraint objective function with constraints. Is this clear or more or less kind of confusing? Because originally, you can say I have C transpose X such that AX greater than or equal to B. And this is what we call primal problem. And then after some conversion, we make this new problem, which is what? B transpose lambda, and then A transpose lambda is less than or equal to C. So the connection between these two problems is through the Lagrangian function x lambda, where you can say the optimal solution would be something like if I have x star, which hopefully will be the solution to this primal problem, and lambda star will be the solution to this dual problem. And you put it in to this, which you can say for this lambda star, my x star is the best. And for other lambda, of course, this has to be also the best. And then for any other x, this lambda star is the best for the dual function. So because of that, then solving this problem, in fact, we can get to the primal problem without any difficulty. Okay, so to make it more accurate, I will say the dual problem is also linear program for this one. And in general, this dual function with respect to lambda and mu is a concave function. But of course, in this case, it's a linear function, so it can be convex or concave. It doesn't really matter. But in general, it will be concave. Do you know why? No clue. The original problem, okay, let's assume that. But that later we are going to say if the original problem is convex, well, we have to make sure that the description is accurate. If we say the original constraint optimization is convex, which means the feasible set is convex. And what? The objective function is convex function. Of course, the constraints are also either convex, and the equality constraints have to be affine. Well, later we are going to talk about that, but these are just mathematical rigors on how we say a constraint optimization problem is a convex problem. convex optimization problem. Then in that case, solving the dual problem won't have any gap to the original problem, to the original optimization problem. Otherwise, there might be a gap, meaning what? Your solution to the Lagrangian function at the dual would be what? Better, unachievable from the primal function. But still, it's an indication on that's like some kind of a performance bound you can use as an indicator. But for now, let's just look at the Lagrangian function. Why intuitively we may expect that the dual function on lambda and mu is concave. Concave means what? This kind of shape, right? This quadratic function goes downward. And convex is like quadratic function upward. And then basically we want to see why intuitively we expect this to be a concave function on mu and lambda. I'm sorry? These are multipliers to what? To the original. Well, remember, I can write down Lagrangian function Lx lambda mu should be connected by f of x plus what? I think lambda is for what? For inequality constraint, so it's g of x, right? Plus mu transpose, and then what? H of x.
Here, for this example, we don't have integrated.
Well, yes, in this particular example, we don't have mu. We have this lambda, and then we say, well, in general, well, just for this example, it's a linear function, right, of this lambda. So it doesn't really matter to us, right? But if you think about for any fixed x, then what? F of x, g of x, h of x will take values more or less fixed. Then what? Then you can say this is some constant, right? And then this is what? The inner product between lambda and g. This is the inner product between mu and h, okay? And then we say this would be a concave function.
Because we are looking for the minimum.
Okay.
This one will always go for the
We've always found to find the minimum. Okay. So we would hope that if it's a concave function, then we can get to that. But why we would expect that? Sorry. Oh, for the minimum, it's convex. Yes. Let me see. So for the dual function, the minimum is with respect to x. And then the maximum is with respect to lambda and mu. So if you fix x, then this would be just, in fact, like what? A linear function of like of this lambda and mu, right? Then we cannot really say too much about that. What we can say is mainly about if f is convex, and hopefully if g is convex, and if h is a convex function, then what? Then the linear combination of that will still be a convex function, right? And then basically there's a hope that we can get to what? The minimum for this whole convex function for any fixed lambda and mu, okay? And then the complementary part, if you try to minimize with respect to x and maximize with respect to lambda and mu, then because it's linear, then doesn't really matter. You make it convex or concave, but because we are trying to, in fact, doing some kind of minimax, so we need the max part to be concave so that we can make sure we have a solution to the maximum, to maximize with respect to lambda and mu. Okay, so you may think this way. If you have some value, let's call lambda star and mu star. If you have this, maybe I call lambda 0 and mu 0. If I have some multiplier that this dual function can in fact satisfy this, meaning that for some value x0, this Lagrangian multiplier does achieve the maximum with respect to your dual function. Then what? Then if you think about this function, this dual function, for any other lambda and mu, in fact, it should be smaller. Right? Well, it's not really by definition, because if you if you have this Lagrangian function, and then what? You dual function, and the difference between what? Between some lambda to this lambda 0, and then for this, you can say these are all another multiplier, right? And if that has to satisfy your Lagrangian function, which means what? Well, I'm trying to say that if you have some dual function that you already have this solution lambda 0 and mu 0, that happens to also satisfy this Lagrangian function for some value x0. Okay? And then I'm trying to say if you choose another lambda and mu, then this lambda and mu has to be smaller than this function, dual function plus this multiplier.
I think you get it from the definition of the LD, right? Dual function, because it involves infinimum. So if you take any other lambda and mu, you have written for every lambda and mu.
Okay.
If you take any other lambda and mu,
Yeah, should be.
there will exist some other points which in between there will be a gap between lambda star.
Okay.
And so we can find that point in between.
But I think the key point is that what about these two terms? They are all just what? The difference of your multiplier to change. Basically, you can think about this is just the difference of your multiplier from lambda 0, mu 0 to whatever other value. Bryce, you want to say something about this? Well, it's the difference between like you multiplier, which is the solution to the dual problem, and also some arbitrary lambda, some arbitrary multiplier that you can pick anyone that you want. So in that case, I would say, like Libby just said, this should be greater than this, right? That's because I'm trying to maximize my dual function and get the solution. But these two extra terms are due to that this dual function is actually what? The solution to the original Lagrangian function. There are some x0 that exists. So that what? Well, I guess it's not that obvious. If you have some function where you'll say this is somewhere below, right? And then let's say if you have another function where you reach the peak. Well, they are in different dimensions. This is one direction. This is another direction, okay? And then I'm trying to say, well, if this point coincides, then we call this point a saddle point. Anyone heard about that? Okay, so basically you can think about this is some primal function, and this is some dual function. And then what? For any fixed multiplier, you can have what? Different primal function. Okay, you can have primal function this, where the minimum is here. You can have another primal function here, where the minimum is here, for instance. Okay, then you can say this is for some lambda 1 mu 1. This is for some lambda 2 mu 2. And this is for lambda 0 mu 0. Okay, and similarly, this is for some x0. Okay, and then I can have maybe another dual function where the maximum becomes here. This is for x1, so on and so forth. Okay. And if what? This point happens to be what? The solution to some primal problem, meaning that if that happens to be a valid Lagrangian function. Meaning what? If I pick this point, is it a valid Lagrangian function which may not be? For instance, I say this it's just find the maximum with respect to lambda and mu, and then you probably cannot satisfy the original Lagrangian function. So that's basically the difference. The nice thing is that if you have this point that tangent to this, which we call that some kind of minimax, or some people call saddle point, then we don't have any problem in finding the dual solution which also solves the primal problem. Otherwise, there will be so-called a duality gap, meaning that your best dual solution probably is not really good for your primal solution, but still you can see how close they can be somehow. Okay, so this basically says if you have a point which satisfies the Lagrangian function, then you can ensure that any other multiplier lambda mu will not be greater than this term, the right-hand side term, including the dual function value, and also what? The difference in the multiplier. And this is also an indication on how you can try to find a good multiplier from some initial guess. Okay? Because this part, you can see that's basically just the difference in the multiplier. Basically, that shows like how close you are to the constraint, right? And you can use that as an indication. If I can, for instance, if I can increase my dual function without violating the constraint, then it's good. I should go along that direction. So you can pursue along that. But in practice, we don't need to worry too much about this part. What we need is to solve the problem so that we can basically use our knowledge of the primal and the duality property to avoid the primal problem if you can. So we say a point x0 and also the multiplier lambda 0 mu 0, we say this is a saddle point if what? If I fix x0 for any other lambda and mu, my lambda 0 mu 0 is what? The maximum. Okay? And then if I fix lambda 0 and mu 0 for any other x, my x0 is what? The minimum. Okay? So if that's the case, of course, if you only look at the right-hand side, that just says this is a stationary point, right? And if, like what Rustin suggested, if f, g, h are convex or affine function, then what? Stationary point should also be the global minimum we are pursuing. And then on the left-hand side, this says what? In fact, we can just maximize the dual variable, these multipliers, lambda and mu, and try to get to this lambda 0 and mu 0 to solve the primal problem indirectly. So on left-hand side, we have maximization problem with respect to multiplier, and on the right-hand side, we have minimization problem with respect to your decision variable, which is standard Lagrangian multiplier. Okay? So the duality theory is just about this statement. If f of x is convex and these inequality constraints are convex function and equality constraints are affine function, well, why we need affine function, which can be either convex or concave, but basically because it's equality constraint, which basically means we can only allow what? Like hyperplane to intersect your feasible set. Other things will not make your feasible set convex. Okay? So that's the reason we say this h of x have to be affine functions. And then, of course, your feasible set has to be a convex set. Okay? Based on that, then you can say this x0 is a stationary point if and only if this x0, lambda 0, mu 0 is a saddle point of the Lagrangian function. So what's the implication of this? Originally, you have a convex minimization problem, right? And because of this kind of nice property, we are trying to pursue what? From the other aspect, from the dual problem, try to maximize the dual function instead of minimizing the primal function. We can do that, and there's a unique global optimal solution at the minimax point. Is that nice? Well, if those things are not satisfied, can we still try to solve a dual problem? In fact, we can. But then the math part will be quite messy because what? Like what I mentioned, we don't know how much the gap will be because those still, this statement is in general right, but what? We don't know what happens when you have the best dual solution and which will have a gap to the primal problem. Let's say if in the primal optimization problem, you minimize your objective function. In that case, for instance, you calculate the Lagrangian, the actual solution should be 100. And when you try your dual problem, maybe you get 95. Then there's like this 5 duality gap. But still, solving this dual problem is useful. Why? For instance, it's very difficult that I can really make sure that my solution, this 100, is really the minimum, right? For instance. But for instance, maybe it's easier. I know the dual function will give me 95. Then this 95 will be what? The lower limit, which may not be achievable, but it's an indication on what? On the best solution, I should hope. Okay, and then let's say in practice, I get 120, which may be close enough to 95. And then, for instance, I may say, well, my algorithm get 120, and then gets 120, that's probably close to my lower limit, close enough to my lower limit. In between how much, I don't know, but I probably should stop. Okay? On the other hand, if you say my lower limit is 5, you get 120, still you think there's a long way to that. And there's a reason to believe that maybe you should improve your algorithm to solve the primal problem, even when there is a duality gap. But in this particular setup, if you think the constraints behave nicely and you are solving a convex minimization problem, then you can try to convert that into a dual problem and exactly solve the dual problem. Will sometimes be easier than solving the primal problem. And of course, for linear program, you can see there's a very nice duality between the primal problem and the dual problem. If the primal problem is a linear program, then the dual problem is also a linear program. And the decision variable changes from what? From the original one to what? To the multiplier. Multiplier is related to what? Just nothing but the constraints. Okay? So basically, you are trying to, in fact, evaluating what? You are trying to evaluate whether a constraint is active or not active. Basically, that's the analogy to what? To the primal and dual problem. So let's take a short break. After that, I'm going to provide maybe 1 or 2 examples to see what would be the benefit of using this duality theory to solve some optimization problem.
does. He's got the best.
Is it genome so much? Is it genome so much?
Who no longer has these
Yeah. So we need like parrots. Yeah.
Yes.
I thought that I'm missing some of my side, and I was trying to see if it was alright for me to send them to your mailbox.
That's fine. I mean, whenever you want to submit,
Okay.
yeah, you just let me know.
Thank you.
Sure.
And that like time the extra word biology, computer science. I mean, it's been proven that algorithms are sort of like a you like it in writing, you don't like it once it gets expressed in paragraph.
Wow.
I like the berry.
Oh, have the computer assignment finished. Good.
I think he's his brother-in-law. Sherry's. But the life moves on. Parents may live 90. So, I don't know, unless somebody takes me out, or I get something really bad, I gotta see if I can top 90, you know? What's that? That's too late, you know? He made it 90. I don't know what's wrong. I'm not complaining, but I need to do my search with that. Well, I mean, my parents were not well, I mean, they were able to make it. Get around. Have enough money when I get there. Just take it easy.
Timing's on, like, it's a conference.
Is that the state academy or the federal academy?
Like, there's a hundred days there, that second time was.
I was telling them that Colorado or there,
Like the last time.
went to one of the American academies, New Jersey, or just a newscast.
There's a way to do it in that lab. Like a way that's more similar.
Okay, so maybe let's continue. Okay. And I think last time Mr. Liu mentioned that he's interested in looking into like a portfolio selection type of problem. And then, of course, I just pick some simplified example to show like how the optimization may play some role in this kind of portfolio analysis. And in this example, let's say we have n different securities with the present prices given by C1, C2 through Cn. Okay, so this you can say maybe just different type of stocks. Maybe you want to invest or whatever. Okay, and I think maybe for those who are familiar with like a basic economy theory, this is very elementary, but it has some implication to what I just explained about the duality theory, and also the way to explain this is very nice about the primal and dual problem. So if we consider at some future time, this stock or whatever security you consider may be in one of m possible states, meaning that, for instance, the price can go up, can go down, and then it can go to maybe m different levels, let's say. And of course, we need to specify that. We say the price of a security type J in state I is denoted by Aij. Okay. And then what? For these n different securities, you want to see if there's any opportunity, what, for you to make some money, to gain some profit, right? Which means what? You want to find some condition, what? Let's assume that you can either buy or sell short, or maybe even try to look into the future to change your holding arbitrarily without encountering any transaction fee or whatever things involved. So basically, you are interested in getting into some state, some kind of portfolio combination, which I call this vector X, which can be positive or negative, meaning what? You can either buy the stock or sell short or whatever. Let's assume you can do either way. Provided what? There's a profit for doing that. And how do you make sure that? Then you can say, well, because I model the security to be in these m possible states, right? And then what? I want my holding what? To be always non-negative, no matter what state it may encounter. Make sense? Then combining this Aij for different possible states, I will have what? I will have m constraints on this n security, which is what? Ax greater than or equal to 0. And then I'm trying to what? Assume that there's a profit, then basically I want to have my holding C transpose X less than 0, then subject to that constraint. Okay? So what type of problem is this? We say this portfolio X is profitable if we can make C transpose X less than 0 and AX greater than or equal to 0. Is this optimization problem? Not really. But if you want, you could say, well, I want to minimize C transpose X such that AX greater than or equal to 0, if you want. Okay? So then it becomes what? Standard linear program. The interesting point I want to make is that in economy theory, there's so-called arbitrage condition. Anyone heard about arbitrage? Nobody? No one? So this arbitrage condition is about what? Whether there exists some profitable condition for this m possible states. If it doesn't exist such a condition, that means what? There's no sure thing for making money, right? If the price goes up, you should do this. If the price goes down, you should do that. Then what? Then you have to make your decision based on the available information. You have to take a risk. But if there is so-called arbitrage condition being satisfied, the implication is what? You can enjoy the free ride without taking any risk, provided the model is accurate. Make sense? So if there is a possibility to make arbitrage, then basically you should take the advantage of doing that. And of course, the question is, what is considered the non-arbitrage condition for this M portfolio? Meaning that this holding will be what? This holding will be more or less stabilized in some way that you can say, well, you cannot make profit out of it, but you cannot also take additional risk on that. So the non-arbitrage condition, later eventually you will see, is what? Deeply connected to what? The dual problem that we explained here. If you write down the Lagrangian function and set the dual problem, where you can see that if you try to minimize Lagrangian function with respect to x, then what? Then the minimum exists under what condition? C should be what? Greater than or equal to A transpose lambda, right? And the critical condition to met is for what? For this lambda to be equal to what? No idea? In this case, what do we have? If you want to minimize this, and then if that makes some sense, what would be the legitimate minimum you can ask for? Remember, x, your decision variable is what? Non-negative, right? Okay, and then what? Of course, this whole thing shouldn't be negative if you want to minimize. You vector u, the inner product between vector u and x. And then in this case, this u is C minus A transpose lambda. Okay, and then of course, the critical condition for this function to have minimum, to have legitimate minimum is what? It's to have C greater than or equal to A transpose lambda, right? And then, of course, we say when C equals to A transpose lambda is what? The transition where, yeah, you cannot have arbitrage, right? It's like we cannot find solution to this to satisfy both inequality constraints. Make sense? Okay, so that's basically like the nice thing. We can use duality theory to easily derive the non-arbitrage condition for this kind of portfolio holding problem. Any questions? No? Anyone think this is useful at all? No? Or it doesn't really matter. So anyone has investment experience from before? No? Do you have any investment experience, like buying or selling stocks or things?
He's a penny stock guy. He likes penny stocks.
Okay. Well, this is about, for instance, if you have maybe let's say your retirement account or some kind of long-term investment, and then you want to analyze the risk or things like that, then basically you put that into some mathematical model and try to find what would be a reliable way to avoid unnecessary risks if you want. It's not really about the immediate way to make profit. Okay, so let's look at another example. And also it's very interesting one. Let's assume that, of course, this is not really gambling, but still it has some real-world implications, and it's a good mathematical abstraction. Let's assume there are n horses in a race, and for a particular horse, let's call horse K, if you bet some value x of K, and let's say the rest public bet S of K, and then let's say if this horse K actually wins the race, and you will gain some value which is A multiply you bet x of K divided by x of K plus S of K. And A is some base value. Does that make sense? Okay, so let's say if you bet horse 5, you put $10. The rest of other students bet, let's say, $100. Okay? And then you bet 10, and the rest bet 100. And then if this horse wins, your share would be 10 over 110, right? 110 multiply some kind of ratio depending on, for instance, whoever is managing the race maybe needs to determine this value A. That's like you're winning. Okay? Is that clear?
That's just your gain without your $10, initial $10.
I'm sorry?
That's just your gain without your initial $10. Right?
That's like you put $10 on the bet, and then the return depends on if this horse wins. Then what? Then basically your return not only depends on how much you put on the bet, also the rest part of the public bets on that horse. Meaning that if everyone put money on that horse, then your share would be small unless you put a lot of money on it. Okay? And this is an interesting problem because, for instance, you have some uncertainty about which horse could win. And then let's say you have probability P of K, you assume, maybe let's say this value could be 0.1, 0.2. You assume there's a chance that this horse will win. And then the question is, how much would you bet?
In order to get the maximal return?
Well, in order to maximize your expected return, yes. In general, you have to say you have some budget, right? Let's say you have $100, okay? And then this A, this winning ratio doesn't really matter because it's just some conversion about how much you will win based on the bet. And also you should know, for instance, horse 1, the public already have some kind of available betting information. Like for instance, horse 1 already has $100 on horse 1, $200 on horse 2, so on and so forth. And also you have some prior knowledge on which horse is likely to win. Okay? So what do you do? Yes?
Taking from my personal experience, I always go for the underdog.
Okay.
Yeah, 'cause, like I was betting on football,
Okay.
and for the beginning of the season now, I kept betting against the Saints,
Okay.
and I kept losing money. But of course, it's like if the public see that the probability that the horse will win is high, everybody goes and bet on it.
Okay.
So your return, no matter how much you put, it's gonna be will never be the maximum return that you're expecting.
Okay.
Because
But still, you cannot ignore like the probability of that horse will win, right?
See,
Because if that horse is very likely to win, then I think the public will bet on that, right?
but if
Would
you
it give
win
odds?
one time,
Yeah.
Give odds.
I do give out, yes. And then this is a legitimate optimization problem, right? Depending on, for instance, do you want to put all your money on a particular horse, or you want to put certain proportion, depending on what? Like the probability, also how much public bets on that, right? The odds, like what you said.
yeah, I mean, over a certain period of time, the money that you win,
Okay.
betting on the horse that everybody think will win,
Okay,
you probably get much more money than that, considering that you're losing money betting on the underdogs every time. But if once in a while the one that nobody expect to win wins, then you get pretty much enough money to cover your losses from the big previous bet.
okay, but that's a different optimization problem, I would say. And also, even if I stick to optimal strategy, would that really make profit? I don't know. Because this is like, on average, I try to maximize my return, assuming that the information is accurate, then my decision is based on whatever the information available, but still there's a chance that I put all things into what I would hope to win, but still maybe like what Brett said, the underdog horse came out as the winning horse, and then I lose whatever bet I have. But let's look at this problem and try to see if you have such a problem, how are you going to put that as a constraint optimization? Of course, the objective is to maximize your return. I say minimize the negative of your return, which is natural. And in this case, it's what? The expected winning, right? So it's probability of horse K wins multiply what? If horse K wins, then how much you get, right? Which is A multiply x of K divided by x of K plus S of K. And then, of course, because it's expected return of your bet, so I have to take the average over all the possible winning on these n horses based on their corresponding probabilities. So I minimize this subject to what kind of constraint? My budget, right? In this case, I will say B is my budget. And then the sum of this xk, which cannot be negative, and then has to be equal to B, right? So I have n decision variables, x1 through xn, right, for my betting. And then I have one objective function, one constraint.
But in the objective function, what is the capital A? Is a measure?
It's just a value.
A value.
Yeah.
Equal for different xk.
Well, it's the same. It's just a conversion. For instance, you say, I bet $10, the public bet 100. If this horse wins, my return will be proportional to 10 over 110, right? But proportion to what? That's some number determined by, for instance, the betting, maybe the dealer or whatever. Let's say the ratio is 5. If A equals to 5, then, for instance, if you bet 10, and then the public bets 100, then if this horse wins, you actually get what? 5 multiply 10 over 110. And then you may say, why should I bet 10? Even if this horse wins, I can only get less than 5. Then that's no good, right? Meaning that in that case, you don't have a legitimate solution to that. Let's say if the value is 50, this A, then maybe you can bet, right? You say, maybe I should bet 100, and the public is also 100. Then what? Even if it wins, then, for instance, if this multiplier is 50, then you think it doesn't worth my $100, right? Okay, so that's basically, this A controls that, like the odds.
But in this case, you cannot really know what is SK.
SK you know. Well, in general, for instance, let's say when you buy this kind of horse ticket, you know the odds. And then here, basically, we assume that you know how much public already bet on that horse. So that you know, for instance, if the public already bets 100, if you bet 500, then you know the odds. Okay.
You mean even if this horse wins, I still lose money?
There's a chance, depending on this ratio A. But there are some horses which could be profitable somehow. If the public doesn't bet anything, then it's like you bet, it wins, you take it all.
Profitability has everything to do with A.
Yeah.
So
if A is a large number.
Well, if A is larger than your bet,
Okay.
then you can make some.
Yeah.
But if it's
You can always make something if A is a very large number. You can always make profit. But still, we are discussing like how much profit would you make by betting how much on a particular horse. You can assume, let's say A is 10 million, so that no matter which horse you bet, you will always make money, let's say. And still, there's a strategy on which way you can get more. Yeah, on average.
But in reality, the A is different.
In reality, you know A.
it's like an A sub K.
Yeah.
Yeah, AK.
There's a different one for each horse. Yes.
Well, in this case, we just say A is fixed to make it easier. If you know A, then you know how to do that. When A are different for different horses. Okay, so this is what? Constraint optimization problem, right? Can you solve for that? Anyone wants to try at least? Do you think that for this problem, there is a global optimal solution to this problem? Yeah, you know this SK, you know A. Of course, you know your budget B. What you need to decide is just this XK, yeah, for each horse, how much you want to bet. Well, if you don't have to always consider dual problem. If you just know this is a constraint optimization problem, you should, first thing first, you should write down what? Lagrangian function.
Yes.
No matter what, I mean, this is the first thing you can do. And then what? Necessary condition, right? Okay, said that. And then what? Try to solve for, yeah, okay. And in fact, that's doable, right? Do you agree? It shouldn't be that hard. I think the level of difficulty.
You might have multiple solutions though.
Well,
You have one constraint.
yeah, you only have one multiplier. Yeah,
Right.
of course, for different, because for different xk, you need to take partial derivative with respect to xk and set it to 0 and try to solve for this, right? And of course, you have like n plus 1 n equations for n unknowns. You should be able to solve that. But still, it's not that nice, right? Because you have n decision variables, you need to solve for n equations to get the stationary solution. And if when n is large, we can think about this is a problem that's usually not scale very well with respect to your decision variables. On the other hand, you always have only one constraint, right? And then what's the nice thing about that, if you think about it? If I can work on the dual function, then what? I have only one variable to work with, right? Do you agree? Which means what? I decompose a large-scale problem into small-scale sub-problems. And then once I solve for the dual, and then I go for the primal, which would be easier in principle, right? But of course, this is just some simplified example. In real engineering applications, you could have millions of decision variables, and they are more or less coupled through some other more complicated constraints. And still, you can do the decomposition if you understand the basic principle like this. Okay, so let's look at Lagrangian function. Okay, so of course, objective function plus what? The constraint. And I use mu, probably it's not really good. I should use Yeah, I think it's fine because it's equality. Yeah, but the budget, you can say I cannot exceed budget. But probably you want to spend all your budget on the betting, right? So it doesn't really matter. Let's look at this. Okay, so of course you have what? If I rearrange a little bit on the objective function and the constraint, in fact, I have the summation k from 1 to n, this mu xk minus this a p of k x of k over s of k plus x of k. And then minus this b mu, which is a multiplier. So why should I do that? Well, if you think about this Lagrangian function, which is the sum of what? Some individual functions of u xk, they are what? Somehow decoupled. You take the sum of this, right? Plus u or minus u multiplier, function of your multiplier. And that's some nice condition. You can, in fact, decompose what? Your large-scale problem into individual smaller ones. Do you agree? Meaning what? You can think about for each xk, I have this function f of xk. I can basically minimize those individually without it, because other decision variable will not affect that. Right? Once I introduce the multiplier into it, given the multiplier, basically I can do the individual optimization. Right? If you give me a multiplier, then I can do that. And once I finish doing that, then what? I can give it back to, for instance, which direction you should go to change your multiplier. So I can always iterate on this. Right? And that's very important numerical technique to decompose large-scale problem into smaller ones by doing so-called primal dual, basically iteration. Something like if I initialize my x1 with some mu, and then what? And then I solve for x1, and then I can do also for this particular mu, which is my initial guess, I can solve for x1 through xn. And then once I solve for that, then basically they will indicate this mu is no good. I should change to another value, right? And then I just keep doing that.
But if you take the value of mu,
I'm sorry?
if you, for a fixed value of mu, if you define these functions,
Yeah.
why the summation will also achieve the minimum if you minimize those functions individually?
I'm sorry?
Why you want to solve that minimization problem with
Yeah.
that summation by considering these individual functions?
Yeah, because if I write, I can say I have somehow f x1 like plus f x2, f1, f2 plus fn xn, right? Right? And then what? I minimize this individually.
But these functions should be non-negative in that case, individually. Otherwise, we cannot say.
I'm sorry?
Those functions should individually be non-negative.
Why is that?
Otherwise, for example, if you
I have n different functions.
and
They are not related, right? So I can just minimize each function individually and find the solution, right? Well, I'm not talking about the dependency. It's just like I could separate them and do the optimization individually. Once I finish, then I can go back. Okay? Yeah, I have to go back to document camera. Whoops, cannot. Okay, so if you think about this dual function, I minimize this function for for different xk, right? Yes? So this is, of course, a function of U multiplier, right? But what? But if you give me some value mu, then basically I can say just for each horse, I try to minimize a small objective function without consider other horses, without consider other decision variables, right? If you give me this value mu, then basically my solution will be a function of mu. Yes? So now do you know how to solve this? I hope so. How to minimize this function? I'm sorry? Take derivative with respect to xk and what? Set it to 0. Okay, and what do you get? Well, now you guys don't even want to do some simple algebra on this. I didn't even ask whether this function is convex or not. That's something needs extra work to verify. You get it? Oh, okay. So how to verify what?
A function is convex.
Well, there are different ways. For this one, I would say just take second order derivative and to see if this,
Always
to see what you get for xk greater than or equal to 0. If it is always positive, then it's a convex function. And that's not hard, I would say, for this function. So anybody already obtained the stationary solution to this? Since I think it's a convex function, so there should be just one solution to that. For given mu a p of k and s of k, your x of k should be what? A function of all this. Okay, I guess the rest thing is waiting for the next page. Now I see that you guys don't like to do this by hand, so I provide you the calculation on this, which I think take derivative with respect to xk. The first term you get just mu and the minus. You get exactly this. Okay, but remember x of k should be what? non-negative. So I just say should be the maximum of 0 and other condition. The other condition is like what I said. If no matter how much money I bet, because of this value A, I always lose, then I shouldn't bet, right? So that depends on what? If you think about the whole thing, that makes some sense. I want what? Square root of A, P of K, what? S of K over mu, greater than this S of K. Okay. So what does that mean? We bet on horse K when this square root of A, P of K, S of K over mu is greater than S of K. And this means P of K over S of K is greater than mu over A. Yes?
What's the numerator on that second term on the partial derivative?
The numerator is A, P of K, S of K, I guess. You get different answer to my calculation. I mean, if you want, I can go to the previous one. Just make sure that you see the objective function and the derivative. Yeah. Well, I would hope that Lippy will actually polish the actual notes. And no, not just the example, but I mean the underlying intuition behind it. Because for this example, I think you can easily follow. But the underlying duality theory behind it, why we need to look from the alternative aspect of the optimization, from the dual function, is important. Because in real life, you probably don't encounter some nice optimization problem like what I gave in the example. You have to find some creative way to write down the objective function and the constraints. Okay, so for this problem, of course, after some manipulation, we realized that P of K over S of K should be greater than mu over A in order for us to bet on horse K. And what does that mean? Well, P of K is what? The probability that horse K will win. S of K is what? How much public already bet on horse K, right? And then A is what? Something like the scale factor, for instance, if horse K wins, like what would be the payoff, right? And then, of course, when you bet, you try to determine the ratio. And what is mu? The Lagrangian multiplier, but what's the meaning behind it in this context? Because in linear program, people call that a shadow price. And in this context, what's the meaning behind it? Well, it is not easy to understand if you don't use your intuition because, for instance, I can follow this condition to say like how many horses I should pick to bet and how much I should bet. But then where should you make a cutoff? In this case, you can see that you know the probability that horse K will win, right? And then also you know what? Like the number of people bet on that, right? And then basically in order to win, you need to know the payoff ratio. And mu is basically somehow the weight on whether you have positive payoff ratio, the cutoff, and the proportionality of the cutoff. So what you need to do is first you need to order your preference on the horses based on what? The ratio between what? The probability that horse will win and also money of public bet. Why is that? Because your winning is based on what? A multiply the ratio between how much you bet and how much public bet. If public bets 0, then what? You just put all your money on that, right? Even though the probability of that horse winning is small, then you should put some money on that. Why? I'm sorry?
If you win, you have a big game.
Yeah, very good. If you win, you have a very big gain. And then even though the probability of that horse is very high, for instance, this P, the maximum value can be 1, right? Close to 1. But then basically, if you think about divided by what? Like how much public will bet, then basically you can see the order significantly depends on what? How much public bets on that. If you don't have any prior knowledge, you can say the probabilities are more or less equal, for instance. But then what? The indication on this is that what? The public bet affect how much you actually gain, right? Make sense? So you order this by, for instance, you can say P1 over S1 is always greater than or equal to P2 over S2 and so on and so forth. So you say I order the horse in such a sequence according to the ratio between the probability this horse will win and how much money public bet is. Okay? And then based on that, I already have this sequence. I already have a preference. Now what? Now I need to do what? I just do what? I need to find this multiplier, but how do I really find this multiplier? That's tricky, right? Because what? It's not very straightforward to do this. If you think about, I will give you an analogy like this. I will say this is the first horse, P1 over S1. This is the second horse, P2 over S2, so on. And then this is the last one, that's Pn over Sn. According to basically my rearranged order, I have this. But assuming that that's basically my ordered sequence, based on this is greater than this is greater than that. The index of horse is rearranged according to this. Then what? Then I need to assign my what? Assign my xk, right? Like how much I should bet. I should bet on this one, right? But proportion to what? well, I need to make sure that if the public bet is, well, maybe I need to draw a sketch like this. If the public bet, this is, for instance, S1, okay? And then I believe that if this horse wins, the actual value, including my bet on this, is actually a P1 and then S1 over mu square root of that, right? That's the value which I put in here. Then what? Then I should bet this much. Okay, and then what? If you think about, if this is, for instance, horse 2, this is S2, then what? If S2 wins, I have A P2 S2 over mu, where that's beyond this by this much. Then I should bet the difference. If this is the whole thing, this is the whole thing, then I should bet only the difference. Okay? Make sense? And then you also want to know, like, how many horses should I bet? That depends on this value, mu. Because I will say I will bet, according to this rearranged order, I will bet the first L horses. And this L should be from 1 up to n, depending on what? On how I find this mu. And this mu will be determined based on what? Based on an iterative procedure, I bet 1 by 2 bet until some L where this mu happens to be equal to this, that can make my budget full. Meaning that, for instance, if you bet 1 bet 2 bet until you bet all your budget, right? And then you stop. Make sense? You bet on horse 1, horse 2, rearranged order on horse 1, 2, 3 until L. At that point, you will not have your budget. You will spend all your budget. Okay? And what's the implication of this? There's an analogy, some people call that iterative water filling procedure. Why it's called the iterative water filling procedure, you can think about.
Water seeks its own level.
I'm sorry?
Water seeks its own level, so
yeah, it's like each horse has some kind of level, right? You have something like you believe the value is this much. If there's a difference, I fill in water, right? And then I fill in another water. And then you just maintain what? The same level until you run out of budget. So some people call that the iterative water filling procedure. For this type of problem, the solution will always have such an interesting structure. Okay, and finally, you may want to verify that this L is indeed the integer that make this happen, that make this somewhere in between, your value proportional to your budget weighted by the public bet essentially satisfy your preference constraint. Okay? So basically, you have this preference constraint, and then essentially there's one condition, meaning that, for instance, when you fill in the water up to a certain level, then you run out of budget, then you stop there. Well, I guess water filling has some kind of analogy like this. If you think about, of course, hose 1 is profitable. You can say it has this. And then you have this, hose 2, hose 3, hose 5, up to hose n. Okay? And water filling means what? When you have some budget, you always fill in what? Here first, right? And then when you reach up to here, then what? You can fill in here. And then basically, L depends on, for instance, this is your budget limit. Then L equals to 3. So that's why there's an analogy called water filling. Like when you spend budget, you always try to bet on the most profitable hose first, and then keep doing that. And eventually, you may say bet more on the hose with large probability to win, and the public thinks otherwise. Well, the solution actually has this kind of preference, right? You believe this horse will have larger chance to win, but what? From the public betting, it doesn't really reflect the actual ratio of your probability, right? For instance, let's say the public betting are all the same. What would you do? You always put more money on the horse that you believe it is likely to win, right? And then, of course, your probability would be weighted by what? By the public opinion, which is reflected on the available bet on that horse. Make sense? Yes? And this example, in fact, has a lot of possible extensions to interesting engineering applications. For instance, let's say if you try to transmit packets through some data network, and you can have different possible routes to transmit your packet, okay? And then what? There's a possible routing problem, like how much flow you want to send through route 1, how much flow you want to send through route 2, and so on and so forth, right? Yes? And then what? You want to, of course, make it efficient, but how to really avoid possible congestion? I would say it's very similar to the problem that we talked in this one, because we need to model what? For each route, what you believe in what? A possible congestion or possible non-congestion condition, right? To transmit your packet. And also you need to know what? Like somehow, because this network is shared by the public, you need to have some way of knowing what the public opinion of this. But of course, the public opinion you cannot directly collect. What you can do is what? Through so-called transmission control protocol, right? And that's basically how you try to adapt your transmission through different routes. adaptively. And in fact, when you try to optimize your routing, it boils down also to some kind of solution very similar to iterative water filling. Okay, so any questions? No? Well, I guess let me try to recap what would be the essence of knowing the primal problem and the dual problem. From this example, what can you see? The primal problem has many decision variables to be optimized, right? And then what? The dual problem is relatively easier because, in fact, in this particular example, when you write down the Lagrangian function, the primal problem automatically decompose into what? Individual objective function which involve with only one decision variable as a function of your multiplier, right? And why is that? In order for that to happen, what kind of requirement do you need? Your objective function is the sum of the individual one. You calculate the expected return for your bet, right? That's the objective function. It has to be decomposable. Not only that, what about the constraint? Well, the constraint has to be decomposable, meaning what? It has to be the sum of the individual variables, so that later when you convert to the dual problem, it's easily decomposable. Okay? So I will try to write something like this. I will say, if you think about, I have L x lambda, which you can say it's actually what? L1 x1 lambda plus L2 x2 lambda plus whatever ln xn lambda, right? And that's important because what? You can solve them individually, and then you have a coordinator that just supply what? The information about the multiplier, right? Well, once you have that, then you let each individual computer to solve small-scale problem, right? I think the linear program was invented, I think, in what, 90, well, earlier than that, 1940s. I think 50s, that's probably right. And then at that time, I think people can handle maybe a few thousand decision variables. And that's considered already significant breakthrough. I'm sorry? Now I think if you're working on like operation research problem, people routinely work on linear program for about, I think, at least above 80% of computational power dedicated to solving linear program type of optimization problem, compared with the whole optimization as a class. And these decision variables easily go thousands or even a few million. But in that large-scale problem, it's not really you solve the whole problem as a big one. You try to decompose them into some small-scale problems, and then you do this so-called dense-wolf decomposition, which is based on so-called duality theory. You can do it for linear program, for convex program, for even some other type of program that you can do. And for the term project, which I already post one term project topic on Blackboard, so that for those of you who are still thinking about what should I do, of course you can always have your option to work on that one, which is also an interesting problem that related to how you can sketch an image by a few measurements. For instance, the image is 256 by 256 grayscale image of like 256 grayscale levels. And what you can do is to maybe just take a few thousands or maybe 20,000 samples of this image and try to recover from only this incomplete or highly inaccurate because of the quantization from this kind of highly sketchy measurements through some optimization technique to try to recover the image from a few measurements, of course, as few as possible. And that's an interesting optimization problem because the number of decision variables will be, I think, a few thousands, at least above 65,000 to be exact. So some small scale technique would not work. You need to really consider some good technique to solve this kind of problem. And of course, I will provide detailed information if you decide to work on that subject. Okay, and also about the computer assignment, I believe some of you already finished and some may not. And some just maybe want to run the MATLAB code that I supplied, which I don't think that's the purpose of learning the unconstrained optimization technique. What I would expect you to do, of course, is to either write your own program, like what Rustin always prefers to do, or maybe take a look at the example sample MATLAB code and try to understand the meaning of it and make some appropriate modifications and try to at least get to the best solution for each algorithm. For instance, the sample design for gradient descent or maybe for conjugate gradient descent may not be tuned towards the best choice for the problem that you're going to solve. So I would hope that at least if you understand better, you can do a better design, at least for each algorithm, and maybe compare about their performance based on how many iterations, and also try to record these iterations either by showing a table, or maybe some of you sketch a plot on, for instance, how to start from a value, getting into a stationary point, so on and so forth. I do hope that after you finish this assignment, at least you feel comfortable about using MATLAB to do small-scale optimization problem for unconstrained and later for constrained optimization. And right now, I try to provide maybe even ahead of time the future homework assignment just for some of you who are keen to take a look what you expect to do. I think you can. And I have new homework assignment posted on Blackboard as well, so you can take a look. And I guess that's pretty much what I intend to cover at this point. Any questions?
This problem can also be solved by the dynamic programming, right?
This problem, why do you think it can be solved by dynamic programming?
Just like the problem we had for the package.
You mean knapsack problem? And that's different because in general, dynamic programming is for so-called discrete optimization problem where the decision has to be made in multiple stages. And of course, the objective is the sum or whatever, the cumulative return from each stage. And also each stage, you only need to consider finite possible states. Like you have the cost to get there so far and then the cost to go.
The only problem is
and in this case, we have continuous decision variable. it is a continuous constraint optimization problem. The difference is that the primal problem is in general difficult to solve directly. And the dual problem is easier. The reason is that the objective function is decomposable somehow with very nice properties. But in practice, it may not be as nice as this one, but still it could be if you want to make it happen by introduce some ancillary variables, which is also a standard technique to handle complex optimization, which I hope if I have time, I may want to talk a little bit on that one. Okay, so I guess we should thank Lipi for taking care of the notes, recitation notes, which I believe is some important effort to share with your classmates in that one. In that regard, I'm trying to also prepare a small trophy for her. I hope that's
Thank you so much.
That's something to at least keep good work, and also keep other students motivated. Okay, so thank you very much. And I will stay here for a couple more minutes. If you do have some questions to discuss, feel free to talk with me. And also, I think next time I plan to talk a little bit about some advanced discrete optimization technique, which I believe is very useful for a lot of applications, but it's a little bit mathematically involved. So I will try to prepare maybe not like this, maybe some presentation slides, but still may need someone who's willing to take recitation notes. So next time, I will try to cover a little bit on so-called submodular function and its minimization, its maximization or minimization problem, which is like the discrete counterpart of convex or concave programming for continuous decision variables. So I'll see you next time.